Right, so for exponentials, so let's just start by looking at what the form of an exponential is. And so the general form is y equals a times an exponent, and this exponent here is b to the x. With a can't be 0 because if it is 0, we don't have an exponential. And also b has to be a positive real number. So our base is not going to be a negative number. And b is not equal to 1. And again, if b is 1, we no longer have an exponential. So basically what we have to know for this lesson is that the generic form for an exponential is y equals a times an exponent. We'll call that b to the x. So here I have 3 examples for you to look at. So in this first example here, my a value is 0.5. The base is 2, and 2 is raised to the power x. In my second example, and notice I'm using function notation for the second example, I have an a value of 2 and a base of 0.5, and then it's raised to the variable x. In each of these situations, notice where your variable is. The variable is always going to be sitting in that power position on that exponent. So let's look at that starting amount. The starting amount is going to be our leading coefficient. So the value of a is going to be where this function is starting. In other words, where is the input equal to 0? So this is also known as the y-intercept. So for this example here, it says determine the y-intercept for the following exponential. Basically, all we have to do is look at what the a value is. My a value is 2, therefore my y-intercept is going to be 0, 2. My interpretation of that is just going to be that the starting amount is 2. That's where we begin when our x is equal to 0. Now, exponentials come in 2 different forms. We either have a growth or we have a decay. And how we know the difference is by looking at what's known as the growth factor, and that is the value of our b. If the value of b is known, the value of b is known as the growth factor when the b value is greater than 1. If my b value is between 0 and 1, then it's decay. Now, I'm going to skip over this decay rate for just a second and just come down here. So basically what that looks like for our exponential growth, when we have a b value of greater than 1, you'll see that this value of b is really expanded as 1 plus r. And the definition above is explaining what r is. R is basically known as either the growth rate or the decay rate. It is basically the rate at which the data is changing. Now, with an exponential, we note that the rate that we're changing is not constant like it is in linear. Whereas linear, you're either increasing by a fixed amount or you're decreasing by a fixed amount. In exponentials, it's either increasing or decreasing by a percentage. And when we use a percentage, that means that each occurrence that we are increasing or decreasing, that value is going to be changing. So R is known as the rate at which the data is changing, and we find R by looking at B. B is defined as 1 plus R. The value of R is expressed as a decimal in our equation, but in a word problem, you might see it represented as a percent. We can calculate the R by just isolating the R. In other words, just take the value of B and subtract off 1 and multiply that by 100. That gives us our percentage. So in this example here, I have an exponential that says y equals 2 times 0.5 to the power x. So in this example here, the b, known as and since this is less than 1, this would be my decay factor. So my decay factor is 0.5. Now from that, I can calculate my decay rate because it's going to be the value of b, subtract off 1, so I get negative 0.5. So really what that means is, multiplying that by 100, it means that the data that I have for this problem is decreasing at a rate of 50%. So that's how we would interpret that. I know there's a lot of like definitions here. It'll make more sense when we start looking at some physical examples here. All right, so what do the graphs look like? So if we have an exponential growth, you're going to see a graph that is trending upward. We call this an increasing graph. And you'll notice that the exponential growth starts out very slow and then it rapidly increases or suddenly explodes is the way that they listed in our Desmos activity. So using that example up above where my base is 2, we see an exponential growth. Now, on this right-hand side, we have an exponential decay. So here, the exponential decay, it drops off rapidly at first, and then it starts to level off. That is what happens when we have a B value that is less than 1 but greater than 0. So we have something, and this will be similar to like half-life, things like that. You probably have seen that before in a science class or even in an economics class. But decay is when our value is really 1 minus r, which is going to give us a value less than 1. Just like with our linear, we have our independent variables and our dependent variables. Our independent are going to be those inputs. My dependent are going to be the outputs. This is the same definitions as we had for linear. The other thing I just want to point out, just like last week, is function notation. Sometimes you'll see us use y. Sometimes you'll see us use like f of x or f of a, s of x, t of t. Basically, what we're doing is this is more of a descriptive label for the problem that we're trying to solve or model. And we're using a function notation to explicitly show you which variable is the input and which variable is the output. Um, any questions about all of those definitions I just threw at you? If you have one, feel free to put it right in the chat. All right, before we start looking at examples, I want to show you a couple other things when it comes to exponentials. And that is exponentials sometimes are written in what's called a natural exponent form. And that is basically there's a number. We have Euler's a number, and this is a number very similar to pi. Like on your calculator, you can find the value of E. But on Excel, we can just type in here. If you put equals EXP, this is telling you this is the exponent e to the power 1, and it will give you its value right here. Anyway, so e is a number. It is equal to approximately 2.72. I can get more digits. Really, there are lots of digits here for this one. If I take my wrapping off here, let's see. I can expand the value of this number, and we have an infinite number of digits that E has. Sometimes when we look at our exponentials, and you probably have seen this in your class, is that when we're using Excel to create these exponentials, it puts it in this E format as opposed to the format we just saw over here to the left, that y equals AB to the X. And so we're going to have to learn how to convert from this E format into that AB to the X format. So this is an example of what it looks like when we have E in the problem. You'll know you have it because you see E, and then there'll be a variable that's going to be on the power of that base E. That's how we know we have an exponential using E. Now, there is a conversion process that we will have to do in this unit that will convert that E value into the B value, so that growth factor or that decay factor. And so notice that up here, what I've done is I've just kind of laid it out for you. We have A times E to the kx. Well, K is just a constant number. E is a constant number. So basically E to some number is just a number. So we just need to figure out what that number is. So in order to do that, we have to isolate that E to the K. So in other words, let's take parentheses, put it around e to the k, and then we're going to convert it by substituting it into Excel and let Excel do the calculations for us. I'm going to use 4 decimal places once I figure out that amount. And then I'm ready to rewrite this in terms of my standard exponential form. So let's take a look at this first example here. So here, this is the given problem. We have 0.5 e to the 2x. If I want to write this in our standard exponential form, I'm going to separate the 2 from the x, and I'm going to attach the 2 with the e so that I see that my base is e, its power is 2, and that is going to represent the value b, either my growth or my decay factor. Now, I'm not expecting you to know exactly what this is at the very beginning. This will be a growth because the exponent is positive, but you may not know that right now, and that's okay. So we can assign e squared to b. Now to calculate the value of this b, what I'm doing is I typed out the formula over to the side. I just typed in exp, that's my exponent, and my power is 2, and I hit enter. And that gives me the value of your b. So now I can rewrite this equation. See if I can highlight it here. So I can rewrite this equation as 0.5 times 7.3891. I'm carrying it to 4 digits, raised to the power x. So the equation I started with is equivalent to the equation that I've ended with. But you'll notice that they're written in 2 different forms. This is written in that natural exponent form, and this is written in the standard exponential form. So let's try this for this example here, because this is something that we're having to do in this unit that normally we need some practice with. All right, so in the second example here, we have f of x equals 2 times e to the 1.567x. So we need to isolate that information. So I'm not going to try to use formulas here, but I did to format this. I'm just going to say we have 2, and we're going to have e, and that's going to be raised to the power 1.567. And I'm just going to put parentheses around that. And that's going to be raised to the power x. So everything we have here in parentheses is going to be the value I need for b. So that means b is equal to e to the 1.567. And I can calculate that amount by typing in equals exp 1.567. So this is the value for my b. So now I can retype my equation here. If I can just edit this formula here. So I can take away all of this. And instead of having e to the 1.567, I'm going to put in 4, let's put some parentheses around that. We have 4.79225. And actually, if I just do 4 digits, that would just be a 3, wouldn't it? So 4.9723. Sorry, 7923. All right, you do the same thing for this last one here. If you want, just list out your b. What is b going to be equal to? You want to put that in the chat. We have b is equal to e to the negative 2. So we're going to calculate that amount by typing in exp. We're going to put in negative 2 as the input. And then I'm going to truncate that decimal to 4 decimal places. And I'm just reusing, I'll copy that formula, just formats it a little bit better. I'm going to put in 0.1353. So, like again, both of these equations are equivalent. They're just written in different forms. Now there is some rounding here, but if we keep it to 4 digits, it should be pretty close for the digits that we'll be looking at in this class. Any questions about that type of conversion? All right, so we're going to do some sorting again. We did this last unit. Here I have some equations, and you should be able to drag these around. I want you to drag these into the appropriate category. For example, this x plus y equals negative 0.44. I need for you to classify this as linear, exponential, or other. Now, since we have done linear, we should be able to determine that this one is in fact linear. So I'm just going to drag it and leave it right there. You have lots of different examples down here. I want you to go through each one of those and sort them out. And then I would like for you to copy and paste your answer in the chat. We were able to do that last time together as well. And that helps me to see what you're getting. So how do we copy? If you have snippet or some sort of screen print, you may use snippet. So we hit new, and then I can just grab that. It will copy it to your clipboard, and then what you can do is just come into your chat and hit paste, and then that's how you can share what you have on your Excel. Now, if you don't have snippet, you should be able to download it, or you may have another type of screen print on your computer that you can use. So I'm going to give you a minute to sort those out. All right, so for this one here, did anybody put this one as an exponential? We have another exponential right here. We have a linear. This one is an other. This one is also an exponential. This one is a linear. And then we have these two. Now, they're an exponential from the sense that by definition, they represent an exponential term, but are they an exponential equation? So where do we put this one right here? This 2.5 times x to the fifth. Would you consider that an exponential equation? The answer to that is no. We will not put that as an exponential. And the reason for that is because my variable is the base as opposed to the exponent. So an exponential equation is going to have x as the power on that exponent. All right, what about this one here? We have y plus e squared equals 5. I only see one variable in this one, and that's the y. And we'll notice that y is not a power on the exponent. In fact, remember e is just a number. It's 2.72 and some change, and we square that, we just get another number. So really, this is a linear. Funny looking linear, but this one is indeed a linear. Anybody have any questions on that?
Yeah, so why was the other one, that's y equals 2.5
Mm-hmm.
parentheses x exponent 5. Why is that one in other, not exponential?
Yeah, the reason why I'm putting it in the other is because this is actually what's called a polynomial. It has to do with where the base is. Since my base is the variable, that makes it other. You'll notice that over here in my exponentials, my x is the power of each one of those. See what that x is, each one of these? So
Oh,
one,
okay, yep.
yep, that's the reason.
Thank you.
Mhm. All right, so let's practice evaluating exponentials using Excel. So here it says, use Excel to evaluate each exponential value. Now, all of these are exponents by definition of what an exponent is. These are all just expressions, so we just want to evaluate each one. Now, when you have a base of e, you're going to evaluate it by using the exponential function in Excel. And you'll see right there when you start typing, a little menu pops up. It says it returns e raised to the power of a given number. So in the parentheses, we're just going to put that given number. So that's negative 0.1592. And we hit enter. And that gives us the value of that number. And this is the equation I used to get that. Now for this next example, this is different than the previous one. And that's because my base is not E, my base is 2. So how will I evaluate this if my base is 2? Well, we type equals and we say base 2, and we're going to use a caret symbol. And inside of the parentheses here, I'm going to put the number I'm raising that base to. So that's 0.1592. So it's slightly different if we actually know what the value is. It's a finite integer here. So we have 2 to that power. So we type 2 to the power. If it's an exponent, meaning base E exponent, then we need to use the exponent function inside of Excel. All right, for our third example, this is going to be EXP. I'm going to put 1.15692. And we get this number here. All right, I see Stephen is typing. Do you have a question, Stephen? So your question might be, well, what happens if I just do e to the, oh, on my end, I see little bubbles, so it looks like you're typing. What if I just said e to the negative 0.1592? It gives us some sort of error message and it says name. It does not know what you mean because, and that is in fact that variables, when you type them in, they translate as text. And so if we have a letter like we do with E, E is not a variable, it's actually a number. And so that's why we have to use the EXP function. All right, let's scroll along. And let's practice expanding these exponentials. So when you try 3, it says write each exponential function in expanded form. So I want you to expand the value of b. So I want you to express b as 1 plus r. Now, when I say 1 plus r can be positive or r may be negative. So let's do the first one together. So we first need to figure out what the value of b is. So we know that b is equal to 0.14 in this particular equation. But how do we calculate r from that? Well, since b is equal to 1 plus r, that means r has to be equal to b minus 1. This is how we can rearrange our variables, solving for the one that we want. In this case, we want find r. So to calculate the value of r, let's put in r 0.14 and subtract off 1. Guess I didn't do that, did I? So we're going to calculate that. So I'm going to just do it down here. So I have 0.14 minus 1. Let's change this to a number. I need to put equals in front of that. And we get a value of negative 0.86 for your R. So if my R value is negative 0.86, I can write this expanded form. And by the way, how I'm able to type all in this cell is to do a carriage return or like a return inside of a box, you have to hold down your Alt key and then hit enter. That's how I'm able to keep adding there, just in case you were wondering. So this is going to give me y equals 2.1, and I'm going to have 1 plus a negative. So if I have plus a negative, that's just going to turn into a minus. That's 0.86, and that's to the power x. So this is how I can expand this so that I'm able to explicitly see I've got my growth factor, or my decay factor, I should say, because it's less than 1. I have a decay factor. Let's write that there as well, just to look at the terminology. I have a decay factor of 0.14. And then I have a decay rate of negative 0.86. So in expanded form, that gives me 2.1 times 1 minus 0.86 to the power x. All right, let's go ahead and move to the second one. Again, I have another decay factor, 0.5649. I know it's decay because it is less than 1. My R is going to be equal to that 0.5649. Subtract off 1. So 0.5649 minus 1. That gives me a negative 0.4351. So my equation is going to be y equals, my A is a 4, and I have 1 plus r. So again, I'm going to have a 1 minus 0.4351, and that's to the power x. All right, if you haven't already, do this third one and post your answer in the chat. Yeah, so when we have values that are over 1, they're actually a little bit easier to calculate because all we have to do is separate out the addition of 1. So we have 56 times 1 plus 2.099, and that's raised to the power x. Now, going in the opposite direction, it's pretty simple because all we're doing is simplifying what's in our base. So write each exponential function in standard form. So I want you to condense these into, instead of 1 plus r, write it as b. So this one will read, copy this over, We just need to calculate that amount, don't we? So let's do that. So we have 1 minus 0.335. So that means inside of my parentheses here, I have 0.665. This one, I have 6 times 1.253 raised to the power x. And I'll have to do a small calculation for this one. I have 1 minus 0.14. So here we have y equals, and I have no leading coefficient that's explicitly written out. So by default, we know that's a 1. So inside of our parentheses, we have 0.86, and that's raised to the power x. All right, scrolling down to you try 5. It says state the starting amount, the growth decay factor, the growth decay rate for each exponential function in your you try number 1. So rewrite them in that expanded form and then classify each exponential as growth or decay. So why don't we do that? And I might add a little barrier in here. Let me reduce my size so I can see all the things I'm looking at. I'm going to add a line in here just to separate these out. So let's go up to this one here and let's copy those over. So they want us to copy, take each of these exponentials, and they want us to expand them. So I have this one here, I have this one here, and I have this one here. So there's 3 of them. So for each one of these, let's identify the starting amount. So the starting amount for our first function here is going to be 4.5. What is my decay or growth factor? Why don't you respond in the chat? What would you say? And actually, I have a 6 on this one too, don't I? Forgot that. What is my decay or growth factor here? Remember, this is the value of your B, right? So in this case, it's not just E, it's E to the what? So it's going to be E, and we're going to raise it to the -1. So the negative that's in front of the X, remember where we isolate that E to the K? So this is what this value of your decay would be. So this is going to be our decay or growth factor. So if you want, I might just leave it just like that for now, just so you can see what it is. And in fact, let me unmerge that cell. And then let's explicitly write that out. So this would be exp to the -1. So this is its value right here. So that's the value of your B. Now our goal is to, and by the way, if our B value is 0.37, then that tells us that we actually have a decay, which means we're going to have a decay rate. So we need to find that decay rate. So the decay rate is going to be the value of your R, not registered. So how did we define R earlier? We said R was equal to B minus 1. And that's what we did a few minutes ago. We were over here looking at that. So B was equal to 1 plus R, so R is equal to B minus 1. So that means we have R is equal to 0. And actually, this is probably a little bit more than 3.7. So let me expand that to 4 decimal places like we did before. So this is going to be R equals 0.3679. Subtract off 1. Andrew, the recording will be available in this chat, so I don't have to send it to you. You should have access to it since you're here now. And if you, when you come back, you should have access to that recording when it's done, okay? And if you can't, just send me a message and then we'll figure out what to do. So we'll calculate that. So I'm going to just use Excel to do some calculations for me. I'll highlight that and subtract off 1. Let's just change that to a number. So my rate is equal to a negative 0.6321. It's a lot of yellow there. Take that off. All right, so let's write our expanded form. So we have our leading coefficient, 4.56. We're going to have 1 plus our R. So since our R is negative, it's going to be 1 minus 0.6321. And that's raised to the power X. And since we have noted that this is a decay factor and decay rate, this is a exponential decay. All right, I would like for you to try to do one of these in its entirety. So I'm going to put myself on mute while you work through, let's work through the second column here, the y equals 0.67 times 2.14 to the x. I'm going to give you about 2 minutes of alone time trying to work through that, and then I'll start working it. All right, did you have the starting amount for that second one to be 0.67? Your growth factor is 2.14, and this one actually is growth. Your growth rate is going to be equal to R equals your B, which is 2.14 minus 1. So that means our R is equal to 1.14. Now, when we talk about the rate, when we're looking at applications, most of the time it'll give it to you as a percent. So how could we rewrite this rate as a percent? We could do that by writing 1.14 and then just multiply it times 100. Oops, not like that. So this would be the percent, or we can let Excel do the percentage for us by using the percentage button. And if I did that for this last one over here, I could do the same thing. I could highlight this and then turn on my percentage button. This is what that rate would look like as a percent. So whenever we're using it in the problem, we're going to, when we're actually calculating, we'll use it as a decimal. But when we represent it in, let's say, context like interpreting or extracting the data out of a word problem, you'll see it written as a percentage. So the expanded form for this one is going to be y equals 0.67. And we have 1 plus our r, and our r is 1.14. That's going to be to the power x. We said this one represents an exponential growth. All right, let's move on to our third one. Give me a thumbs up in the chat if you have got the third one done already. All right, I'm going to give you another 2 minutes to work on this last one here. I'm going to mute myself. All right, our starting amount is 99.9. We have a decay factor here. Our base is 1/3, which means we're going to have a decay rate. And that's going to be our B value minus 1. So that's going to be equal to 2/3. Now, if we're writing this out, if we do 2 divided by 3, that gives us 0.66. And then we're going to round, that fourth digit would round to a 7. So if we were to write this as a percentage, it would be 66.67%. The expanded form for this one's going to be 99.9. Actually, this should be negative, should it not? I didn't write that out. So it'd be 1/3 minus 1. So that should be equals a negative 2/3. So this should be negative, and that will be negative. Negatives matter. So we have 0.667, because that would give us a totally different answer if we did not include that negative. That's to the power x. And we're back to an exponential decay. Are there any questions on number 5? All right, so now we're going to be looking at some data. So now we're going to take the information we learned from last time we were together, looking at how to graph, and we're going to apply what does that look like for exponentials. So here I have a set of data. I have 5 data points, and we want to determine the exponential equation for the set of data. So first thing we're going to do is we're going to create our table of values. So we have 1 and we have 11,619. Our second data set is 20 and 6,005. Our next set of data is 30 and 3,549. We have 40 and 2016. And we have 55 and 1002. So if you recall from last time, what we're going to do is we're going to highlight this, and we're going to go to insert, and we have to insert our scatter plot, and that creates us our table of values. And if you recall, you can format your table of values. You can select what kind of grid you would like to see. You can also change the layout, putting labels on there. Let's do something like this. So this is going to represent my x. This is going to represent my y. And I'll just call this you try number 6. So now that we have our data, in order to create our graph or find our equation, we're going to right click on a data point and we're going to say add trend line. And by default, we said last time that it will default to linear, but we want to see it as an exponential. So we're going to select exponential, and you'll notice that the curve is changing from a line to an exponential curve. We can see that this curve is trending down. So this tells me that we're looking at an exponential decay. Not only do we need that graph, but we also need the equation. So I've selected the equation. And let's just make it some bigger for us to see. And now we have our equation. So we have y equals 13,404. And I'm going to go ahead and explicitly write out let's make this bigger, my e. So I have e raised to the power negative 0.046, and then that's raised to the power x. So notice that all of that in there represents the value of b. The b value so that's going to be exp. We have negative 0.046. Let's round that down to 4 decimal places. All right, so the questions they're asking me are determine the starting amount, determine the growth or decay factor, and determine the growth and decay rate. So let's find our value of A. So A, which is known as our starting amount, this is equal to 13,404. And let's reformat these cells so that I don't have to keep doing that. We have our value of B is going to be a decay factor. That's equal to 0.9550. And then we need to find R, which is our decay rate. I'm going to have to calculate that. So that's going to be equal to the B value minus 1. And let's see, hold on 1 second. I don't know if it picked up the right value or not. Oh no, it did not. I need this one here. All right, so now we want to write our exponential form, which we have already. That was given to us in the problem. So our exponential form, if I were to write it in Excel, I would just use, and let me just show you how to do that. So if you were inserting a formula in Excel, you would do that by clicking on Insert, and then all the way at the bottom, going past your charts, you would click on Equation. And then since we're doing an exponent, we can click on, it says Script, and it has e to the x. It's just one way of doing it, I should say. Hold on 1 second. There we go. So we have e to the negative 0.046x. And again, we can expand the size of this. We have 13,404 in front of that, and we have y equals. So that's how I can write that in exponential form. You can also copy this and just copy it down. Now to write this in that expanded form, we still have that 13,404. Our R value is negative, so it's going to be 1 minus 0.045, and that's raised to the power x. And we've all determined that this is decreasing, so this represents an exponential decay. Yes, Andrew.
Yeah, so why is wouldn't it be negative negative 0.046 instead of 45 in the
Oh, right here.
oh yeah.
Okay. Because this one says just the exponential form. So this was the exponential form, and I probably should write it as the exponential natural form. This is the way that it just comes from Excel. When you actually ask it to do an exponential model, it will give you the natural form first. So we're just going to write it the way that it's here. So you could have just copied. I don't know if it'll allow you to copy just that field. No, it would copy the whole thing. So basically what I did is I just copied this and I brought it down. So in your lesson, it might be called E form, like in your Desmos lesson, if you're using Desmos. And then in this form here, they call this one the Q form. And we're going to be looking at Q form in just a minute. So this one's known as our E form. Then we have Q form. So I'm using my data that I've calculated up here in order to expand it to show that information. All right, I think that's all I have on this one. So let's go over to the modeling. So we're going to take all of this and we're going to put it together for our module, which is exponential modeling. So if you click over to the next tab, this is that Q form I was speaking of. And so when we're modeling problems, we like to show it in Q form. Sometimes we have it expanded like you see here, and sometimes we have it condensed where that 1 plus R is just written as one number like B. So an exponential model is okay, so how do I know I have an exponential model when I look at a word problem? So this is what you look for. Look at things that are increasing or decreasing by a percentage. If you see that the rate of change is increasing by, let's say, 20%, 100%, or decreasing by 50%, then that tells me I have an exponential model. Now, the percentage rate written as a decimal is going to give you that R value. If we have a growth, that R value is going to be positive. If I have a decay, that R value is going to be negative, and that's what we've seen in that previous tab. The Q sub 0, that means the initial amount. That is the same thing as our A value. So if they tell you it starts at this number, they're giving you that initial amount. In this case, it's called Q sub 0. Or Q naught is another way to describe that. Our input is going to be T, and that's going to be relevant to time. So basically time is going to what we're going to be using going into these functions, and then we're going to have some sort of output coming out of that function. In this case, the output's going to be Q. So we have our independent variable, which is going to be T. Our dependent variable is known as Q. So This is the same formula as what we have over here. It's the same formula as this. It really looks a lot like this, right? It's just that we've relabeled these letters as Q, R, and T. So let's take an example here, and I think I only have a few. I think I have 2 examples that we're going to work through. So suppose they give us the situation where it says a candle starts out as 6 inches tall. It's the same kind of problem we have for the linear, except that the way that it's burning exponentially at a rate of 10% per hour. So we've got input, output. So our input is going to be T. Our output is going to be Q. So T represents time in hours. And I know it's in hours because it says 10% per hour. Q is going to be the height of the candle in inches. Now, what is the starting amount that we're going to use in this situation? Yep, it's going to be 6 inches. All right, if the candle is burning at an exponential rate of 10% per hour, would you consider this to be a growth or a decay? I agree. It's going to be decay. And that's because the height, and how you could explain that is you would say the height of the candle is decreasing by 10% each hour. All right, now we need to find our decay rate. So our decay rate is going to be 10%. So now we need to calculate that as a decimal. So you're going to take 10 and you're going to divide it by 100, just like we did when we took a percentage and turned it into a decimal. So our decay rate, and it is decay, I'm going to highlight that, is 0.10. So now we're ready to come up with our exponential model. Let's first start with that expanded form. And then we're going to write it in condensed. Now, because this is decay, it might be better for us to go ahead and put a negative on there so that we don't forget that it is decreasing. So we have a decay of 10%, because if we don't take that negative, we might end up with the wrong value. Remember, those negatives, those matter. So let's put those in there. So we have our Q formula. So we have Q equals our starting amount. We're going to have 1 minus 0.10, and that's raised to the power t. So this would be the expanded amount, expanded form. If we write it condensed, it would be Q equals 6. And then this is going to be 0.90 to the power t. And also I could write this Q of t as well. A little less concerned about how you format it here, but I just want you to note that Q and Q of t mean the same thing here. Now let's use this model to predict the height of the candle after 2.5 hours. So just like we did with our linear, so our input, so I need to change my variables because we're now in T and Q. So let's change this to T and Q. We're going to start with 2.5 hours. And we need to calculate our output based on that 2.5. So we're going to put in our equation. So we have 6 times we have 0.90 raised to the power of our input. So this is the equation that I'm using right here. So the height of our candle after 2.5 hours is 4.61 inches. Any questions about part A? For part B, it says use this model to predict the height of the candle after 200 minutes. Again, we have T and Q. And since this is in hours, we have some conversion to do. So we have 200 minutes over 1 is equal to 60 minutes, 1 hour. So that would be our conversion factor there. So we can calculate this as 200 divided by 60. So our T is equal to 3.333. And if we're in Excel, it's keeping up with all the digits. It's just the number of digits you want displayed. You can limit that. All right, we're going to put in our equation. And again, I already have my equation stored here, so I might just copy and paste. And when I do that, we can double check our formula here. So it's 6 times the input, 6 times the base, which is 0.90, raised to the power, and it's selecting the cell P22, which is at 3.33. So after 200 minutes, we have 4.22 inches left on our candle. So we're almost a whole hour later, and we can see that it's starting to slow down. And that's what they were saying before about those exponential decays. Decays, they decline rapidly and then they start to slow down. Now in part C, it says, how long will it take for the candle to burn down to 1 inch? So last time when we were working on this together, we did a lot of guessing and checking. So if I just copy my formula again in here, if I'm at 0, we know we're at this. How do I get down to 1 inch? So let's say maybe 15 hours, I don't know, 20 hours. So we could just do some guessing, or we can be precise and use a function called goal seek. Now, goal seek is a tool that's available on the downloaded version of Excel. If you're using the web version, I do not believe that it's available there. So if you would, go up to the top and you're first going to select data. And I am going to do a little screenshot of that for you. So you're going to first select data. Then we're going to select the what if analysis. And I'll just put this in the Excel for you in case someone needs it later. So I go to what if analysis, and then I'm going to select goal seek. Now, before doing that, it's best to go ahead and highlight the cell we're trying to goal seek. So we're trying to goal seek this value here. We want this to be equal to 1. This is what we're trying to get. Is that equal to 1? So we highlight this cell and we go to data, what if analysis, goal seek. And you'll notice that that cell is now highlighted. Now, this will only work if you have your equation already programmed in that particular cell, and I do. I have the formula sitting in there. So we want to change this cell and manipulate it until it turns into the value 1. That's what we're trying to find. And it's going to do that by selecting this as input. Right now I have that set at 19, but it doesn't matter because Excel, when I hit OK, you'll notice that the value starts changing until it gets the right value equal to 1. So what we did was called goal seek. So if I do this right here, let's see, cancel. So just to kind of show you what I have going on here, so that would be the field that I have here. You highlight the field that contains the value. So maybe I should have highlighted, let's try this again. We'll do goal seek. There we go. And now let's highlight that one. We're going to set that equal to 1 by changing this cell here. So how long is it going to take to get down to 1 inch? It's going to take 17 point, let's say 02 hours if we round that to 2 decimal places. And this is how we can do this guessing and checking using a mathematical approach using the tool GoalSeek. Does anybody have any questions about GoalSeek? Stephen, do you have a question? So you say you got a slightly different number. So slightly different how? What number did you get? Okay. All right. So one reason you might get something. All right. So Melissa got the same thing, same as Stephen. Um, let's see here. Do you have the same equation? 6 times 0.9 raised to the power? Same equation? Okay. All right. So it's because the reason is probably slightly different. And again, if I do it again, it might give me something different. Let's say I start here from 0 instead of 19. We'll see if that changes its approach. So I'm going to change its value to 1 by changing this input. Oh, there we go. So there we go. So it changed it slightly different and it made it 0, 0. So there's going to be some room for some error here. And that's because of the rounding that will take place with the exponential. So it depends on where you're starting. So if we start from 0, it's going to give you probably the smallest number that hits 1. And then if you start above the value, it might give you the largest value that will hit 1. So both of those will be correct. So probably for a problem like this, we'll ask you just to round it to the whole number. That way both of our answers would be correct. Or we'll accept a range of values. Thanks for pointing that out. All right, let's move over to our next problem. It's our last one. So I used the same problem in our last time we were together for linear. And here I want to say, well, what would this data look like? Actually, I did change the data slightly, and these are not real values, by the way. The one that we did with linear, those were actual values I pulled off the website. These were inflated just to make it exponential. So here it says we have a table of values that show teacher salaries since 1999. Use Excel to determine an exponential equation that models the data and represents the years since 1999. They want us to define and interpret the values below in context of the problem. All right. So we know that when we have dates, we have to convert these. And so since they're telling us that since 1999, we know this is going to start off with 0. This one's going to be the year 2004 minus 1999, so that's going to be 5. We have the year 2005 minus 1999, so that should be 6. And the year 2006 minus 1999, that should give us 7. So now we have our set of data. You're welcome, Andrew. All right, our input. So we have S and T. This is what they want us to use here. Our starting amount, we don't know yet, but we'll find that out once we graph it, and we can interpret that. So T would be the time. This would be years since 1999. S is going to be the salary of teachers in North Carolina, the average salary. All right, so let's go ahead and get our data together. So we highlight our data and we're going to go to Insert, Charts, Scatter Plot. I'm going to format this. Might use this data. I'm going to reformat it here. So this would be the years since 1999. North Carolina teacher salaries. Maybe I'll take off this. All right. If we are to map out a model, an exponential, we're going to right click. We're going to say add trend line, and we're going to select exponential. And we're going to display equation on chart. So our exponential model that we have here, let me take off my, so we have y equals 29808, and then we have e to the power 0.0975, and that's raised to the power x. And actually, let me change it in terms of our variables. So this should be s, and this should be t. Or if you want to just write it like so. That way it looks more like what you have right here. So now that we have this equation, we can read off our starting amount. It's 29,808. So basically what this is saying is that the salaries in 1999 were $29,808. Now, looking at this graph, we can see that it's trending up. So we know that this is a growth model. So now we need to come up with our growth rate. So in order to find the growth rate, we need to find our the value of b, right? So let's just do this over here to the side. So b is going to be equal to the exponential, and that's going to be to the power 0.0975. So let's exp 0.0975. Let's expand my digits here. So we have a b value of 1.1024. So this is my growth factor. So my growth rate is just going to be this amount minus 1. So my decay or growth rate in this case is going to be a growth. So my growth rate is 0.1024, or you can turn this into a percentage and we get 10.24%. So now let's talk about how to interpret that amount. What does that mean? So this means that the average salaries North Carolina teachers increase 10.24% per year, which is not true, but it is true for this example. So if we were to rewrite this equation in that Q format, we would write this as S of t, or S, equals 29808. We would have 1 plus 0.1024 raised to the power t. And I believe that is our time. Before you head out of here, we do have some predictions that we can do, but it's the same as the one before. What I would like for you to do is please make sure you fill out the post survey. And that ends our time together.